Welcome back, everyone. It's my pleasure now to introduce our featured invited speaker for today, Professor Song Han from MIT. Song is an assistant professor in MIT's Department of Electrical Engineering and Computer Science. He received his PhD from Stanford. Some of you may recall that he presented his PhD work at one of our quarterly member events several years ago. And before that, his bachelor's degree from Tsinghua University. Song's research focuses on efficient deep learning computing. He proposed deep compression techniques that can reduce neural network size by an order of magnitude without loss of accuracy. And also has worked on associated hardware implementation techniques, such as an efficient inference engine, exploiting pruning and weight sparsity for accelerating deep neural network inference workloads. Song's recent work on hardware-aware neural architecture search has been featured in numerous publications and received top honors in several low-power computer vision competitions, including at CVPR, ICCV, and NeurIPS. Song also won the Best Paper Award at the ICLR conference in 2016 and the FPGA conference in 2017. He's received a number of other awards, including the Sony Faculty Award, Facebook Faculty Award, and being named to the MIT Technology Review's 35 Innovators Under 35. Of course, there are thousands of academic researchers working on various aspects of deep neural network technology. The reason why I wanted Song to present to us is his work, I think, is uniquely relevant to the interests of our community because Song's focus is on finding ways to not just make more accurate networks, not just extend neural networks to new applications, but to maximize efficiency so that deep neural networks can be deployed very, very widely. And the combination of that very relevant focus, and I think the innovation and just productivity of Song and his group really make him and his group stand out in terms of importance and relevance to this community. So Song, welcome. Thank you very much for being here with us today. Those in the audience, if you have questions for Song, please type them in the queue using the Q&A button in Zoom. We'll get to as many of them as we can at the end of Song's talk, and then Song will be with us for an additional extended Q&A and discussion period starting at 11:15. Song, it's all yours. Thanks very much.
Okay, thank you, Jeff. Thanks for having me here today. So let me share my screen. So today I'm going to present our recent research, the Once for All DNN, simplifying the design of efficient models for diverse hardware platforms. So we focus on AIoT, basically AI on IoT devices, targeting low power, low latency, and high accuracy. Traditionally, this used to require lots of many engineering efforts to tune the model, which usually are pretty large and contain a lot of parameters and weights and lots of computation. And we want to enable fewer engineers by AutoML and produce small models with tiny ML techniques that require less computation. So these are the research topics from our lab. We focus on tiny ML and efficient deep learning, targeting smaller model size, lower energy, lower latency, and automated design methodology. We work on full stack, from efficient AI applications to automated tools to efficient hardware and also AI for EDA. For application side, we have worked on efficient video recognition, the temporal shift module, which was highlighted by NVIDIA and IBM and adopted by widely industry like Baidu, Paddle, and also the Lab. We also work on efficient recognition, widely used for autonomous driving, currently ranking first on the Semantic Kitty leaderboard and being used by MIT driverless self-driving car team. We also worked on efficient machine translation. We can reduce the design cost by 4 orders of magnitude compared with Google's approach of evolved transformer. Then we build automated tools to optimize and compress deep neural nets. The pruning, quantization, compression has become an industry standard I also co-founded DeFi Tech, which was acquired by Xilinx. So far, we have produced 2 generations of automated neural network architecture design methodology, the proxyless NAS, and also the OFA, which is the focus of the talk today, which has been adopted by Facebook PyTorch and also Amazon AutoGlow. Such AI designed by AI has consistently outperformed the human performance, achieved several awards in low-power computer vision challenge, MicroNet challenge, and visual vigorous challenge. And finally, we build specialized hardware supporting pruned and sparse weight, which has been used by many silicon companies. So we focus on this full stack research from edge to the cloud, algorithm to hardware, and training to inference. Here is a list of publications. So the problem we are trying to solve is tiny ML come at the cost of big ML. Tiny ML for inference, big ML for training and architecture search. There is an article from MIT Technology Review showing the severe effect of the high cost of training a single AI model can emit as much carbon as 5 cars in their entire lifetimes. So this is a paper from Google, evolved transformer, taking a lot of computational power to search an efficient model. So we need green AI to solve the environmental problem of neural architecture search. So compared with the evolved transformer, which takes 626,000 pounds of CO2 emission, our approach can reduce the cost by 4 orders of magnitude, but achieve even superior accuracy 1 year later. So the challenge here is, given the large design cost and the diverse hardware platforms, an efficient design methodology is very critical. Otherwise, the GPU hours and design cost is going to grow linearly with the amount of devices we are going to support. For example, a mobile app developer has to support both a brand new Galaxy S10 phone and also a pretty old Galaxy X4 phone. How do we design efficient neural nets that can run on all these hardware platforms? Not to mention the cloud AI, the big difference between cloud AI computation capability versus the tiny AI computation capability. And our solution here is to build a once-for-all network, train one network, and specialize it for efficient deployment. Okay, as illustrated in this figure, we are training a single model, the once-for-all model, that is a mother. You can think of it as a mother network. It can born many child networks. And we can get many children nets for free. We don't have to retrain the weights, and they can directly be deployed. For example, on the data center, we can grab a larger subnetwork. On the mobile phone, we can grab a smaller network. On the microcontroller, we can grab an even smaller subnetwork and achieve the Pareto optimal. And the beauty here is, no matter how many scenarios you have, like 3 in this case, we don't have to retrain for each scenario. And the design cost for the once-for-all network is fully amortized when you have several different scenarios. Even if you have only one hardware platform, like the mobile phone, you may have different scenarios where in the morning, the battery may be full, so you may want to run a larger network. In the evening, the mobile phone may be in low battery, therefore you may want to run a smaller network, but doesn't sacrifice too much of the accuracy. And in the middle, there is a smooth change that we can enable by using such once-for-all network rather than storing many replicas in the phone. And the key difference, this is a technical slide, that enable such low training and search cost is by decouple training and search. So conventional neural architecture search NAS method require a meta-controller. On the left-hand side, when you have many devices, you have to each search several episodes, and each episode you have to train from scratch, or forward and backward, which is pretty expensive. And after you find a good model, you have to do post-search training again to train the architecture. Our solution is by decoupling training and search. So we pay the expensive training over only once, And then during search, no matter how many devices we have, how many search episodes we have, we just grab the weights directly from the Westphal network without any training, without any forward and backward. And then we run just sample from the OFA, and if it's a good model, then break. And we can directly deploy without any training. So by decoupling training and search, we can save a lot of computational budget. And later we find this method also improves the accuracy since different sample networks share the weights. So the smaller model can achieve a better accuracy than training individually. So again, a Westphal network for the GPU, larger model; for the phone, middle-sized model; for tiny microcontroller, smaller size model. And you don't have to retrain for each scenario. So the challenge here is, this is great, first of all, but the challenge is how to prevent different subnetworks from interfering with each other, okay? And the solution here is by progressive shrinking. We force the different subnetworks to share the weights. For example, the smaller network share the weights with the larger network. And we progressively shrink across 4 different dimensions: the resolution, the kernel size, the depth, and the width. So we train the full model first, and then we fine-tune by progressively shrinking across the 4 dimensions. And then we fine-tune both the large and smaller networks and repeat this process until it converges. So this method is similar to network pruning, but quite different. In pruning, it only shrink, for example, channel pruning only shrink the width dimension, and you only fine-tune the smaller net. And here we shrink across 4 different dimensions, and we fine-tune both the large and the small networks. And when you are fine-tuning the large network, the smaller networks also get improved because they share the weights. Vice versa, when you are fine-tuning the smaller network, the large network also gets improved because they share the weights. So here is the animation. We first allow elastic resolution from full resolution to partial, and then elastic kernel size from full to partial, and elastic depth from full to partial, and finally elastic width from full width to partial width. By using this methodology, the accuracy can be significantly improved by roughly 3% on ImageNet. Without progressive shrinking, the accuracy is much worse. And the key highlight here is we train only once, but we can get many subnetworks. Like in this figure, we measured it on the Samsung Note 10 mobile device. The latency ranges from 6 milliseconds all the way to 24 milliseconds. And y-axis is the top line ImageNet accuracy, ranging from 67 to 77. Okay, and the baseline here is the state-of-the-art MobileNet version 3 from Google. Okay, the trade-off curve, there are 4 points. In order to achieve these 4 points in the blue curve, the MobileNet V3 has to carefully tune the hyperparameters for each scenario and train 4 times. Like the scenario we mentioned, when you get up, the mobile phone is full battery, you can run a larger model, higher accuracy model. But as the battery gradually dies away, you may want to switch to a smaller network. But how can we train only once and get many for free? And that's our solution, where you see many dots. There are more than 10 dots on the red curve, and we only train them once, and we can get many for free. And the Pareto curve significantly dominates the MobileNet version 3 with respect to latency and lower latency and higher accuracy. So how is this search achieved? We just talked about training the Westphal network with progressive shrinking. Since we decouple the training and the search, the next step is to search from the OFA network. And we just use evolution or even random search. So in order to quickly measure the figure of merit with respect to both accuracy and latency, we build a model twin, which is accuracy and latency predictor that is very accurate. So it's a machine learning model that can The feature is the network architecture, a one-hot encoded network architecture. And the prediction is the latency and also the accuracy, so that we don't have to physically measure the latency, but use the machine learning model to predict the latency. And we don't have to train the architecture from scratch, but just predict the accuracy as well. And here, the predicted latency is highly correlated, actually pretty accurate with respect to the real latency, very close to y equals to x. So we can get a very quick feedback. As a result, we can outperform, after the search, we can outperform the EfficientNet and MobileNet 3 by a large margin. On the left-hand side is the latency measured on Google Pixel 1. The blue curve is the EfficientNet, which they aggressively used a very complicated hyperparameter tuning for the learning rate, etc. But we use this very simple hyperparameters, actually no other hyperparameter search, but consistently achieved like 2.6 times faster inference latency and 3.8% higher accuracy compared with the EfficientNet. And compared with MobileNet version 3, we are 1.5 times faster, or achieving up to 4% higher accuracy without sacrificing the latency. And we find the training from scratch of the search architecture cannot achieve the same level of accuracy. So the green curve here is showing the accuracy. If we just use the search architecture but train it from scratch, it's going to it still outperforms EfficientNet and MobileNet version 3, but not as good as the OFA model. And this is because the weight sharing, again, like we mentioned, when you are training the larger model, the smaller model share the weights. So it also gets improved. And progressive shrinking is a very effective method to prevent larger and small models to interfere with each other. So this training methodology is also helping improve the accuracy. So this is a very thorough comparison of the accuracy versus the amount of computation. You see the size of the circle indicates the model size, and the x-axis is the number of computation, the y-axis is the accuracy. We want a smaller circle, smaller model, smaller number of max, so higher accuracy. And ideally, we want some points that is right here. If you see something familiar, you may see less than 50 is right here, 4 billion max, 76 top point accuracy, and we are right here, only less than 600 million max, but we can achieve an 80% top point accuracy, which is better than like EfficientNet, Proxyless NAS, our first generation of NAS, MobileNet version 3, DenseNet, NASNet-A, ResNext, or even the exception, which is 14 times less computation. And in general, we find the models produced by AutoML, which is indicated by an asterisk in the middle, outperforms those models that are handcrafted. Like everything with a circle inside, they are handcrafted. But these are AutoML produced models. So in general, AutoML produced models achieve better trade-off than the manually designed model. And among those AutoML models, our model is showing quite significant improvement. So thanks to our collaborators, we have measured the latency on diverse hardware platforms using only one model. For example, on the top, all these 3 platforms on Samsung phone, this is Samsung S7 Edge, Google Pixel 2, LG G8, they are using exactly the same once-for-all network, but we search different subnetworks from the once-for-all network, and they consistently outperform the MobileNet version 3. And MobileNet version 3 has 4 different, you have to train 4 times, but for all these devices, we only train once. On the bottom is MobileNet version 2, since V3 has a special layer not supported on FPGA. Once-for-all network works consistently well on the GPU, CPU, and even FPGA accelerators. For example, on the FPGA accelerator, we can achieve a higher accuracy, 69.6 top line, but reducing the latency from 6.3 milliseconds to only 4 milliseconds. So this is without any change in the hardware. our methodology is widely applicable to a wide range of silicon devices, be it CPU, GPU, FPGA, or even DSP. Okay. So this is a DSP result on Qualcomm Snapdragon DSP. We received the first place in 2 consecutive low-power computer vision challenges, and we can achieve a latency of only 5.15 milliseconds with a top 1 ImageNet accuracy of 78.8. So these results show the general applicability on diverse hardware platforms. So one network, diverse hardware platforms, once for all. Okay. So this is a deeper dive into OFA on the FPGA platform. So in collaboration with Xilinx, we measured the arithmetic intensity and also the measured GOPS per second using the Xilinx Vitus AI. So we can our search model achieves 40% higher arithmetic intensity, meaning that it's less memory bounded. So you move the same amount of data, but now we can do 40% more arithmetic. Okay, arithmetic is free. Memory is very expensive, so it's very worthwhile to increase the computation over the same amount of data movement. Okay, and as a result, we can achieve a 47% higher measured GOPS per second on the same silicon, same architecture. So it's very important to match the neural network design with the hardware architecture design. So these are the results. Our specialized search AI designed AI on different hardware platforms. They are quite different. For example, on the FPGA, they only use choose to learn to use only 3x3 kernels, which is highly optimized. On CPU and GPU, they use the 3x3, 5x5, and also 7x7. And you see the GPU model tend to be wider since GPU has more parallelism. So we have released a tutorial for our first generation and also the second generation of NAS, Proxyless NAS, and also OFA. So this is an advertisement. We had the tutorial in CVPR. We can do architecture search with 1 GPU in only 2 minutes. So I highly recommend you check out this tutorial and help design specialized models to help building a better product on your silicon. If you are a software company, then you can build a better application, more efficient application for your app, especially when you have diverse deployment scenarios. For example, here we can apply it to many applications like video recognition, 3D vision for autonomous driving, and also GAN compression. For video recognition, the purpose is to recognize people's action on mobile devices. Since privacy is important, we want to run them locally. And on the right-hand side, we can reduce the computation by 7 times compared with the baseline method, or we can using the same amount of computation but improve the accuracy by 3%. So this is a latency comparison of our model for video recognition, much faster than the baseline model. And this is a throughput comparison, doing video classification and recognizing those actions and activities. We can have up to 12.7 larger throughput compared with the baseline. And the model is even more accurate. For example, when doing object detection compared with per frame detection on the left, which give error saying it's a train due to the high beam light, our model is very robust. It's showing it's a car throughout the whole video because it has temporal modeling capability, not per frame modeling. And this is a demo that's showing our gesture recognition can run real time on a Jetson Nano, a $99 mobile GPU to recognize your gestures and move and control the Google Map. For example, you can swipe, and also you can stop, and you can thumb up to enter the street view. It's running 30 frames per second, locally, everything running on a Jetson Nano. So talking about TinyML, I just added a few slides talking about scaling up. So we also have researched on large-scale distributed training using the Summit supercomputer. We can reduce the training time from 2 days to only 14 minutes, 200 times measured speed up by scaling this distributed training to 1,536 GPUs. So conventional models are difficult to scale up because they have a large model size, means a lot of gradient. Gradient is equal to the model size to exchange. And our model has much smaller model size and also less gradients. So saving a lot of communication bandwidth, also much fewer flops, saving the GPU hours, and also much smaller number of input frames, saving the disk bandwidth. So networking bandwidth, disk bandwidth, computation are all saved by our efficient model. Next, once-for-all network can be applied to compressing GANs. So this is a cycle GAN turning a horse into a zebra. On the left-hand side is the baseline. It's running pretty slowly. As you can see, only 12 frames per second. On the bottom, it already finished. It can run 40 frames per second, 3.3x speed up compared with the baseline. And the quality isn't hurt at all. So this method is pretty effective accelerating the GANs. Let's watch the video again. Pretty slow on the top, and pretty fast and smooth on the bottom. So this enables interactive image generation and also image rendering, image style transfer across videos. Another application is efficient 3D recognition for point cloud. So in AR and VR, we don't want to have a whole backpack of computers. For self-driving car, we don't want to have a whole trunk of GPUs. So we need to reduce the computation and make lightweight models. So our recent paper on ECCV20 called Sparse Point Voxel NAS neural architecture search can achieve 4x computation reduction and 2x speed up over the Stanford Minkowski net, ranking first on the semantic kitty dataset. So this is the comparison of the error map. So the red on the right-hand side is the error. The top is the darknet segmentation. So taking 40 million parameters and 370 gigaflops. Our model is only 1 million parameters and 10 gigaflops. So much fewer computation, but also less error. And this is showing the speed comparison. The baseline model is running that require 114 gigaflops versus ours is only 30 gigaflops, 3.4 frames per second versus 6.45 frames per second. So LiDAR is usually considered expensive, both for its price and also for the computation processing. So we enable this lightweight LiDAR, efficient LiDAR perception for self-driving cars. And this method has been adopted by MIT Driverless, a team for self-driving car. And in particular, this method can achieve less error, particularly on those small objects like person and also the pole, the bicycle, as you can see from the error map in red. The less red, the better. So this is very safety critical. Conventional method taking so much computation cannot afford to detect those small objects. So our method achieved a great balance between computation and also accuracy. Not only segmentation, but also detection. We can produce less duplicated predictions using less computation. Okay. All right, so in summary, our dream is to make AI efficient with tiny resources. Tiny means not only less computational resource, but also less human resource, since human engineering is very expensive and very, machine learning used to be very labor intensive. In particular, we proposed several hardware-aware AutoML methods and a push-the-button solution for a diverse range of hardware platforms. And here are a list of publications you can dive into detail. So we aim for design automation for AI, and also another effort is on AI for design automation. published in Deck 20. Few news media. Finally, the technical summary. We proposed the once-for-all network, efficient inference for diverse hardware platforms. We present an effective progressive shrinking approach for training the once-for-all model. Okay, surpassed the MobileNet version 3 and EfficientNet by a large margin. Several awards, and we also open sourced more than 50 different pre-trained OFA models covering CPU, GPU, FPGA, and DSP. You can download for free. You can try it for free. If you're using MobileNet version 2, I highly recommend you can try this model. Much simpler to deploy, much better performance. Okay, it's tailored for different hardware platforms. And if you're interested to search your own model, you're welcome to check out our full-fledged tutorial that can do an architecture search on only one GPU in only 2 minutes. Okay, everything is available on our project page. With that, I want to thank you and hope we can build a brighter future together where we have a tiny AI and efficient AI. Here are the more links to our GitHub. All our projects are open source. You are very welcome to contribute. And today's talk and slides are available also on YouTube and also my homepage. And thank you all for your attention.
Thank you very much, Song. Super, super interesting work. And as I said in the intro, very relevant to this community, given the focus here on how we enable practical implementation of deep learning and other forms of edge AI for deployment in the real world with real cost and power and size constraints.